All right, welcome to Lincoln Physics. Here we are today. We're going to learn about constant velocity, which we have over here, and we're going to learn about constant acceleration, which we have over here. We notice that when we have constant velocity, when we have constant velocity, we have three variables. We have our velocity that's in meters per second. We've got our distance, which is going to be in meters, and we have our time, which is going to be in seconds. We notice that we can create three equations, and anytime we know two of the variables, we can solve for the third that we don't know. So very straightforward. We know that when we have constant velocity, that the acceleration is zero, and we also understand that the net force on the object is zero. So we say we're at equilibrium. On the other hand, when we're not at equilibrium and we have an acceleration, if that acceleration happens to be constant, then we've got a little more complicated situation. You'll notice that we have to talk about an initial velocity, which is the velocity at the start of the event, and that can be positive or negative depending if it's going in the direction we've decided to call positive. We'll have a final velocity, which is the velocity at the end of the interval after a time t, which means we need the t for the time. And then obviously it's constant acceleration, so we have an acceleration. And again, that one might be positive or negative depending on if it's going in the direction we've decided to call positive. So here we have our constant acceleration equations. I should just take a second and note that there's another one that you can use that comes out of this equation. Okay, if we pretend that we have constant velocity, and we go ahead and we can say that delta x is equal to vi plus vf divided by 2 times time, you'll notice that we get an equation that is going to disappear because I really don't want us to use it. But if your teacher likes you using that one, go for it. It doesn't have acceleration in it. I prefer this set of equations to use since those are the ones given on AP. But in any case, let's go ahead and start the problem. So it looks like we've got two cars. Car A has constant velocity. It's moving at 25 meters per second the whole time, including at time equals 0. So it has a running start. It's already moving as it crosses the start line of the race, which is a bit unfair. Car B, on the other hand, is starting from rest like you're supposed to, so its initial velocity is 0. But as soon as car A goes zipping by it at the start of the race, it starts accelerating. And it's accelerating at 8 meters per second. So its velocity is just going to keep getting bigger and bigger by 8 meters per second every second. So eventually its velocity will be bigger than the 25 meters per second that car A has. So we know it'll catch up to car A eventually. The question is, will it make it in time? Let's see after 5 seconds how we've done. Okay, so we'll start with car A, which is the easier car to think about. Since we know the 25 meters per second and we've been given the 5 seconds, it's pretty easy for us to just go ahead and plug in 25 meters per second, 5 seconds, and that enables us to solve for this 125 meters that car A will have gone in the first 5 seconds. On the other hand, we've got a little harder situation for car B. Car B started from rest. It has this acceleration of 8 meters per second squared, and we know that we want to use this set of equations to solve it. So what we're going to do is we're going to organize what we know, which is very helpful. So we notice that the initial velocity is 0. We know that because it started from rest. We don't know the final velocity. We do know the acceleration because it was given. We do know the time since that was what was asked in the question. And we do not know the displacement, which is what we want to know because we want to know if or not it's gone farther than the 125 meters that car A went in this initial 5 seconds. So you'll notice that we know 3 of the variables. Okay? And there's 5 variables, 2 of which we don't know. And whenever we have 2 variables that we don't know and 3 that we do know, we are going to be able to solve the problem. And so the question is, using the 3 that we know, can we pick the right equation and then solve for the ones that we don't know? And you'll notice that since VF is not known, right, and delta x is not known, that we probably don't want to use this first equation, because this first equation has delta x in it and it also has VF in it. That's not going to be all that helpful. Okay, but looking at the other equations, we can go ahead and solve for other variables that we don't know. Since it's distance that we're trying to know, I'm going to go ahead and use this equation here that says that delta x is VIT plus 1/2 AT squared. Because I know everything on the right side of that thing, it's going to be very simple. Okay? Anytime you know every variable within equation except one, so here, for example, of all these variables, I know all of them except one of the variables, then it's easy to solve for the one you don't know. You'll notice that I've gotten a little sloppy when I plug and chug here, that I haven't put the units in. You'll notice back in the other one here, I put the units in, and I didn't do that here. And that's okay. It's okay because I've made this table of values where I've shown what my units are, and so I can get just a little sloppy and not show them. So we plug those numbers in, plug it through, and we can see that we go 100 meters. Now 100 meters is not as far as the other car went, so we can say with confidence that after 5 seconds, car A is still winning. Okay? Let's see what happens after 200 meters, though, which is the finish of the race, and we'll see who has won at that point. Okay? So we're going to do very similar things. This time we know different information. This time we have the 200 meters that we know, and we still have our 25 meters per second over here, which was the velocity. So I can go ahead and plug and chug through this easy equation, and we can get our 8 seconds is how long it's going to take for the car A to go those 200 meters. Okay, let's see how car B did here with its acceleration. Again, we want to organize our information, so it's a little different this time. The initial velocity is still 0. We still don't know VF. Okay, the acceleration is still 8 meters per second. This time we don't know the time. Okay, and delta x is 200 meters, and that should say meters. I'm going to go ahead and solve for VF first. We could really go straight for the time first and end the problem quicker, but I want to make a point about the final velocity here. So I'm going to go ahead and use this equation right here. We notice that we know the initial velocity, we know the acceleration, and we know delta x, so we can go ahead and solve for VF. And the point I want to make is when you use this equation, you needed to take a square root. And whenever you take a square root, you want to be careful to use either the positive or the negative. But in this problem, since everything was always going in a positive direction when these two cars were racing, we go ahead and we use a positive value here for our VF. But be careful on that. On some of the harder problems, you need to, on your own, decide to use the negative or positive there. In any case, we'll notice that it's going a lot faster than the 25 meters per second that the R was going. So we'd expect that there's a chance it caught up and passed it. Let's take a look. The last thing we can do here is just look to see the amount of time taken. At this point, it's easy to just use VF equals VI plus AT, and we get our 7.1 seconds, which is less time than the 8 seconds, so that's sweet. And we know that car B passed car A and won. Another tougher question would be to ask yourself, at what time did those two cars pass each other? See if you can figure that one out. In any case, I'm off for now, and hope this helped a little bit. And let me know if you have some questions, and I'd be glad to help you. Thanks a lot.